Hi, BC Calc. These are your day 76 notes. Today, we are going to start talking about some exponential applications, all applications that you're familiar with, but you will be wowed and amazed by the way we can develop some formulas that you know and love using calculus. So we'll get into that in just a few minutes. But first and foremost, we have to recall if f of x and g of x are inverses of one another, then we know that the composition of those functions in either direction, f of g of x or g of f of x, would result in x, right? If one undoes the other, then the result is that input of x. So what I want to do is show you how we can get that inverse relationship with derivatives one more time by showing you that if we start with this relationship right here and we take the derivative of both sides, then what are we left with? Well, the derivative of the left side, you're going to, when we have a composition of functions, be using chain rule, of course, right? So the derivative of the inside is going to be g prime of x, and the derivative of the outside function would be f prime of, leave the inside alone. So that's what's going to be on the left side using just quick chain rule there. And the derivative of x with respect to x is 1. So therefore, we're going to really quickly get our rule here that if f of x and g of x are inverses, dividing f prime of g of x to the other side, we see that g prime would equal 1 over f prime of g of x. So in general, if we think of these values of a as a's and b's, we know that g prime of b is equal to 1 over f prime of a. So we definitely have this sort of reciprocal relationship, but we have to make sure that the value that we plug into the inverse is the output on the original function. So we have to figure out what is that corresponding input, and then the reciprocal slope of that tangent line at that coordinate would give you a relationship for the inverse slope of the tangent. So that's just kind of a quick recap, but just a little bit of a different approach to get that rule. You'll see we have two practice problems here. One relates to this concept of finding the derivative of an inverse function. You'll notice maybe just a slightly different notation, but it's the same idea as calling the inverse function g and finding g prime of -8 there. And then find dy dx for this example, now that we know our lovely derivative of e to the x. So go ahead and try those two before I see you next. Those shouldn't take too long. Let's move on to the next page, which is some applications with compound interest. Here we go. So this should be a very familiar formula to you. A of t equals p times 1 plus r over n to the nt power. This is a formula for interest compounded a certain number of times per year. So to define some of those variables that I have up here for you, we know that capital A is the final amount of money you would have in your account. It makes sense to denote that A is a function of time here. We know that capital P is the principal. Principal is known as the initial investment that we're putting into an account. We know that R is going to be defined as the annual interest rate. When you plug in that interest rate, we're going to, of course, plug that in as a decimal. In this formula, t is definitely time in years. Of course, other exponential applications, we might be looking at units of time in other quantities, but for compound interest, t is a time in years. And then n is kind of the big piece. N is the number of times interest is compounded per year. So I think a common misconception when you first learn this formula is if I say interest is compounded quarterly, let's say. If your interest rate is 5%, it doesn't mean that you get 5% each quarter of a year. It's that that 5% gets divided into 4 equal pieces and applied in 4 increments throughout the year. And when you divide up that rate, by the end of the year, you've received your annual rate of 5%. But the fact that it got split into some pieces would be more beneficial for your account to grow faster than, let's say, if interest was just compounded annually once at the end of the year. So to that effect, see if you can quickly calculate then if we have $1,200 compounded quarterly at an annual interest rate of 9%, how much will you have after 5 years? So use that formula up above for compound interest, plug in what you know, see what your investment is worth after 5 years. I'm going to show you my answer here. So if you've done that already, Plug in 1,200 for the principal, the initial amount. Rate gets plugged in as a decimal. When interest is compounded quarterly, we're looking at n equals 4. And we know that the time is 5 years. So when all is said and done, 5 years later, we have earned $672.61 in interest for a total of $1,872.61. Now, if you're thinking about the interest rates in your savings accounts that you might have some money in right now, put a decimal point in front of the 9, and that's probably the rate that you have in a savings account, 0.9%. It is most likely nowhere near 9%. The type of account you might be investing in here, might have something to do with stocks or bonds or mutual funds or other things that maybe you talk about in econ, but definitely not your good old savings account. All right. So moving on from there, of course, you've heard of other compound interest formulas that relate to thinking about what happens as n goes to infinity, right? If we compounded quarterly or monthly or daily, as n gets larger and larger and larger, in other words, as n goes to infinity, what we find is that the formula that's at the top, 1 plus r over n to the nt, remember the quantity 1 plus 1 over x to the x, as n goes to infinity, is approaching e. So we're going to start being able to later on prove the PERT formula, which is just so awesome, right? I mean, we take it for granted. We use it when we say that interest is compounded continuously, which is what you should have written on the next line here. Interest is compounded continuously. We're definitely using PERT. But we're going to eventually, in 7.5, which is nearby, be able to prove the PERT formula. So if I calculate how much you would have if interest is compounded continuously, a of 5, go ahead and type that into your calculator with the same given information, same initial amount, same rate. 1,200 e to the 0.09 times 5 years. You can see it's not that big of a difference. I mean, again, you're still getting 9% at the end of the year, but it's cut into kind of like an infinitely number of small pieces. So it's not even quite $10 more 5 years later. But if you had the option between the two accounts, of course, you're going to pick the one in which your money grows the fastest. So PERT is going to always win out under the conditions where you have the same initial investment, same rates, same amount of time. Okay, so hopefully you know and love these formulas and you recall them. There's something that we can do that's kind of interesting as it relates to talking about specifically doubling an investment. So if you turn to the next page, that's I would say a pretty common question that we get when you're first learning this concept in Algebra 2 and in pre-calc. How long is it going to take to double your investment? So that's going to be dependent, of course, on the interest rate. But if we think about just always the concept of doubling, hang on.
The new teacher meeting is going to be in the main office conference room. Again, the new teacher meeting will be in the main office conference room. No pressure if you can't make it. Thank you.
Okay, if you heard that announcement from Mr. Clark, the new teacher meeting is in the main office conference room, and no pressure, but good thing I'm not a new teacher. Okay, depends on the interest rate is what I was saying. So we want the end amount to be 2 times the initial amount, P. So let's set it up. So if I plug in 2P where there's a P, or where there's an A of T, I should say, we want to figure out how much time it takes. So we're going to solve for T. So we're going to divide that P over to get 2 equals e to the RT. And to solve for T, we're going to take the ln of both sides. So ln of T would equal R times T, right? ln of E to some power is just the power. And then dividing by R, we get ln of 2 over R is how much time it takes. So to make some more context of this, ln of 2 is approximately 0.693. So if you multiply the top and bottom by 100, thinking of those percents that we're typically given anyway when we're told what a rate is. If you multiply the top and bottom by 100, you get 69.3 over 100R. So in general, you can round that a little bit and approximate that if you want to know how much time it takes for your money to double, it's approximately 70 divided by 100 times the rate. Okay. So if I wanted to figure out how long would it take to double at 7%? 7%, when you plug in the rate, in this case, you're plugging it in as the decimal 0.07. So it's going to take approximately 10 years for your money to double. 70 over 7. And if you look at a rate of 10%, 70 over 10, when you plug it in, is going to be approximately 7 years to double in that instance. So if we think about in general what we're kind of building towards here, it's just going to be 70 over whatever the interest rate is. And it really, I guess, is the interest rate times 100, right? Because if you're truly plugging in that interest rate as a decimal, we want to multiply that by 100. So the rule of 70 is what we're getting at here. So it's a really quick way of determining how long it takes to double your money. It's just 70 divided by the interest rate, which we've proven by using that approximation for ln of 2, which is pretty close when you multiply by 100 to 70. So if you're not looking for an exact amount of time, this is a good general rule of thumb to figure out how much or how long it takes to double your money. And again, the interest rate is whatever that rate is times 100. So pretty cool stuff, right? Let's go ahead and move on to some more exponential applications. Because of course we don't always just talk about money growing. Sometimes we talk about like biology, populations that grow, other applications in economics. In general, if something increases or decreases at a rate that is proportional to the amount present, we can consider the following variable definitions. Okay, so you'll see that in this relationship over here, dy dt, the rate, is proportional to, sometimes you'll see that represented with a little alpha here. So this symbol, although I don't think it's very commonly used, if you see that used, it's saying that the rate is proportional to y, which is the amount present. So the variables that we're going to define for you is y is the quantity, the amount present, t is the time, and y sub 0 is the quantity at time 0. So we know that if there's some proportional relationship, that dy dt, the rate, equals some constant k times the amount present y. And the initial condition is that y of 0 equals y sub 0. So this then starts to turn into the solution to a differential equation. Now, in order to differentiate here, what I'm going to do is I'm actually going to separate this. And then from this derivative, we're going to take the antiderivative of both sides. So what I'm going to do is I'm going to swing the y to this side, like divide y over here, and then multiply the dt to this side. So we get dy over y equals k dt to start. Okay, so we're trying to figure out what is an equation for y when we have something that's increasing or decreasing at a rate proportional to the amount present. So then from there, take the antiderivative of both sides. Well, we know what this is, right? 1 over y dy would be ln absolute value of y. On the other side, what we're going to wind up getting is, since that's some constant of proportionality, k, with respect to t, you would get a result of kt there. Okay. Now, since these are both indefinite integrals, you would really have plus c and plus c. I'm going to just move all the constants to this side and write a big plus c on the right side. Okay, so we have that. So if we have the ln absolute value of y equals kt plus c, we can convert this to exponential form by knowing this is base e, right? So it's going to be that y is equal to e to the kt plus c. Now keep in mind, we know that the initial condition is that y of 0 equals y sub 0. Okay, so if you were to plug in 0 for t, that's going to equal the initial value, the quantity at time sub 0. So if I do e to the 0 plus c up here, we know that the initial is e to the c. Okay. So if we have this information, what I want you to do is come back over here to our equation for y. And maybe I can convince you using some exponent properties that this is equivalent to e to the kt times e to the c. All right, we know if we multiply two things that have the same base, we would add those exponents. So these two things are equivalent. But oh wait, e to the c, I mean, c is some constant, and base e is 2.718. So this is just some constant value. So therefore, we get y equals some constant c times e to the kt. And what is that constant really equal to? That constant is y sub 0, the quantity at time t sub 0. It's your initial amount. So we get y equals y sub 0 e to the kt. Isn't this thus then proving what we now come to know as things like the PERT formula, things like population growth and decay? It's all those things. The other familiar forms of this equation are things like what we just worked with, PERT. Another familiar form that relates to population growth and decay is something of the form n of t, which would equal some initial amount n sub 0 e to the kt. So when you have in a given problem that a rate is proportional to the amount present, you don't necessarily have to set up a differential equation. We know that the solution to this differential equation will always result in these exponential application formulas that we're familiar with from Algebra 2 and from pre-calc, which I think is pretty fantastic. Okay, so the keywords that you're looking for, again, is that we have a rate that's proportional to an amount present. We can jump right to using one of these formulas and therefore be able to calculate usually how much time it takes for something to happen. That's, of course, a pretty common thing that we're interested in. But before we do anything else, just the last example here, we will say for class tomorrow. So this is talking about the rate of a disease that's spreading, which I guess is kind of ironic, but we'll talk about this a little bit more in class. Here's the scenario. Okay, suppose that in any year, the number of cases of a disease is reduced by 20%. If there are 10,000 cases today, in how many years will there be only 1,000 cases? So we're going to be solving for that aspect of time. Like I mentioned before, we will talk about that example tomorrow in class. So pretty theoretical today, just in terms of thinking about exponential applications, but we're now going to start taking some more specific scenarios and applying what we talked about in today's notes. So let me know if you have any questions next time I see you. Otherwise, we'll be working on the stopping to spread the disease next time I see you. Have a good one.